Nothing says Friday night like tree diagrams and conditional probability in the basement. So let's do it. All right. So here's our context. Everything we kind of try to learn, figure out today, we're going to do through this context. So give the video a pause, read that. So we're given it's estimated that if a random driver is speeding, there's a 12% chance that he or she will receive a ticket. If the driver is not speeding, there's a 7% chance he or she will receive a ticket. And it's generally estimated that about 60% of drivers speed. So there's a lot to soak in here, right? A lot of numbers, a lot of different probabilities. And one kind of different question I would ask you, or will ask you, do you think that receiving a ticket and speeding are independent, and why? Or, in other words, do you think that receiving a ticket is related? That would be not independent. Is getting a ticket related to speeding, and why? We'll save that topic for another day. Today, we want to start to look at how we can model situations with tree diagrams. And this is one of those situations. So some kind of generic notes for you to take here. So a tree diagram is I just forgot how to speak English. A tree diagram, right? When do we use one? So if we're given some kind of sequence of events, right? One thing happens after another. It turns out I don't know how to spell one. Should have just stuck with the math, right? Then it suggests we could use a tree diagram, right? And that's what we have here. So we've got two things to consider. We've got to think about, does someone get a ticket or not? But the chance they get a ticket or not, right, changes based on whether or not they were speeding. So to know whether there's a 7 or 12% chance that you receive a ticket, first, we have to know if you were speeding or not, right? So we've got a sequence of events here. We've got first person speeds or not, then they either get a ticket or not, right? So one event happening after another. So that suggests to me we could use a tree diagram. Another thing to think about is if we're given conditional probabilities, then we're probably going to be using a tree diagram. So if I jump back to the context here, we're given some conditional probabilities, and we'll come back to this idea kind of later when we look at the actual tree diagram. But here, right, this 12%, that's the chance you will get a ticket if we know you're speeding. This 12% is the probability you get a ticket given we know you were speeding, right? And then over here, similarly, this 7%, this is the probability you get a ticket given you were not speeding, you know, because there's other stuff you can get tickets for. So the fact that we're given conditional probabilities, maybe that's a little harder to recognize than the sequence of events, but that also suggests that a tree diagram might be a good way to model a given situation. Some other general stuff about tree diagrams, and this like maybe isn't going to make a ton of sense until we actually, you know, do the math and look at it, but just some stuff to add to the lists in the front here or in the beginning. So we're going to multiply across branches when we work with a tree diagram. We'll see that. The probabilities at the far right should add up to 1, whatever that means. We'll take a look. And by the far right, I mean these and probabilities you'll see. So we're going to want to check that those sum to 1 to kind of check our work. And then we want to remember the probabilities that are shown on the branches are conditional probabilities. Really, it's kind of on like the second set of branches. But again, when we create the tree, we'll look at what all these red things mean. Here's a picture of a tree diagram and a cool baby. Probably didn't need that, but well, actually here's a sample tree diagram. We could model a couple coin flips, right? So for sequence of events, one flip, then another. Here, for probability to flip, first time is heads 0.5, right? Tails 0.5, heads and tails 0.5. This spot would represent the probability that you get heads and tails. So just to see that example, maybe you create the tree diagram. Pause the video right now. Try it out. Take a look at this scenario, and based on that kind of little example so you can see how it's structured, can you create the tree diagram for this situation? I bet you can. One little tip, put some words on it. Don't just put numbers, label in words what each spot represents. Pause. And now that you're back, let's try this thing out. So as we start to create our tree, we want to think about like what happens first, or like what depends on what. Here, right, whether you get a ticket or not changes, or related to, maybe it's related to, I don't want to give away that first question, but whether you get a ticket or not, that probability changes based on whether you were speeding or not. So to know the probability you get a ticket, 12 or 7%, first we have to know if a driver was speeding. So our first kind of set of branches here, saying kind of a lot in inappropriate ways. This is not kind of branches, they really are. So a person is either speeding or not speeding. So now as we construct this, probability someone's speeding is 0.6. So what's probability someone's not speeding? That's right, 0.4, right? So anytime the branches split, the values on the branches that split have to sum to 1. So another way we'll see that. After a person's speeding or not, now we want to think about, did they get a ticket or not? And so similarly, where these two green branches split, these two numbers should sum to 1. So we know if you're speeding, there's a 12% chance that you're going to receive a ticket. So of all the speeders, sorry, I just got to like color code my underlining here, OCD. 12% of people who were speeding got a ticket, which of course means 88% did not. And again, right, just subtract from 1, these have to sum to 1. And then lastly down here, you got this, right? So if you're not speeding, still you can get a ticket or no ticket. And if you're not speeding, there's a 7% chance. Be careful with that 0. Don't put 0.7 on me. That will destroy everything. 7%, 7 divided by 100 is 0.07. And then so that means 93% of the people who are not speeding don't get a ticket. So there's our basic tree diagram to start. Now, one of those red bullets on the previous slide said that the second set of branches are showing us conditional probabilities. So these numbers all in green and purple, these are all conditional probabilities. Right, we already touched on, like, this is the probability someone gets a ticket given they were speeding, not a tick. It would probably be hard to get a tick if you were speeding. Down here, right, like this is the probability someone gets a ticket given they were not speeding. I know we already did those two on the previous slide, so you do the other ones. You got that. And I'm sure you paused it and now you're telling me this is the probability someone does not get a ticket given they were speeding. And then, right, this is the probability someone gets no ticket given we know they were not speeding. Which makes sense, right? Like the probability you don't get a ticket if you're not speeding, it seems like is, should be decent, fairly high. Speeding's probably the most kind of common kind of ticket, at least based on these numbers. It seems to be that is the case. All right, so let's get back to the math. I'm going to get rid of all this red stuff just so it doesn't kind of get in our way. I did it again, kind of. I meant literally get in our way. What is happening? Friday night. I'm tired. It's a long week, guys. You know how it is. Hybrid learning. Come on. All right. So whenever I'm making a tree diagram, I want to find these 4 far right probabilities. These probabilities on the far right, these are all and probabilities. By that, I mean, so this first spot, or you think about it, right? Oh my God, you can pause the video. That's crazy. You do that. And then try to figure out, like, this is blank and blank, blank and blank. So like this black spot, whatever number we get here, this is going to represent the probability that any random driver is speeding and gets a ticket. Now that's much different than this green number. This green number is of the speeders, 12% get a ticket. This green number is only out of all the people who are speeding, 12% get a ticket. This black number that's going to be right here, this is out of any driver. So I don't know they're speeding or anything, just any random driver. This is going to represent the probability any random driver is speeding and then also gets a ticket. And of course, you should pause and fill in the rest. Right, and this is the probability someone's speeding and then does not get a ticket. This is the probability someone's speeding and then, and gets a ticket. Wow, you can't even read that. And then, but you can listen. And this is the probability someone is not speeding and does not get a ticket. Think about this before we find these values. Which of these do you think should be the highest probabilities? Just thinking kind of logically. Which should be the lowest probabilities? Let's see if what you think is what happens. So when we work with a tree diagram, we multiply across branches. You don't have to necessarily write the multiplication on the AP exam. It's implied that you multiply across branches, but at the same time, it's not a bad idea. So for this spot right here, speeding and ticket, we're going to do 0.6 times 0.2, which is 0.072. So if you just roll 0.072 here with no multiplication symbol, that's okay. It's implied that it's multiplication. For the sake of our notes, I guess I'll do it in a different color. No, I'll have to keep going to the orange. That's annoying. So this is 0.6 times 0.12. What would this one be? Well, I got the orange out. Oh yeah, I agree. 0.4 times 0.88. This spot's going to be 0.4 times 0.07. And this spot's going to be 0.4 times 0.93. And so that's going to give us 0.528 for speeding and no ticket, 0.028 and 372. I paused for a second because I was trying to think to myself, does it seem reasonable that the probability someone's speeding and gets no ticket is larger than this? But for a second, I forgot these weren't conditional probabilities. These red numbers, right? They're not just out of the speeders. These are out of any driver. So it makes sense to me that the largest percentage is just people. I guess that means I'm assuming a lot of people speed, but are people who are speeding and then don't get a ticket. And generally, right, the majority of drivers don't get a ticket. I wonder why I'm saying that. Maybe that's one of the questions later. One of the things we always check, or I always like to check, these red numbers here, now that we found these far right probabilities should sum to 1 on that previous slide. If I try to add these up, these should add to 1. Because these are this is the whole sample space. If you're a driver, these are the situations. You're either speeding and get a ticket, or you're speeding and you don't get a ticket. Or you're not speeding and you get a ticket, or you're not speeding and you don't get a ticket, right? That's every possible outcome. So these probabilities should sum to 1. I promise I checked. They do. If you don't believe me, look right here. I did all the math. I did all the problems. All right. So that's our tree diagram. Questions? I didn't think so. But I do wish I was in the room with you guys doing this, and you did ask me questions. That's way more fun. All right. If you're just some random person watching this video, I know that this is number 2, but my students, we're going to jump to number 2 first because number 1's actually a little harder. We'll see. So this is just the tree diagram at the bottom, right? We just created that. As we start to do the math with these, start to answer the questions, until you get more comfortable with these types of problems, one little tidbit of advice, other than showing words on your tree, you're going to do all the problems with these far right numbers. There are other ways to do them, other ways we could take shortcuts, but in the beginning, when you're getting comfortable, or if you're struggling at all, right, that's maybe a safe kind of backup plan. It's just, you're going to answer all the questions with the numbers in the purple box. For instance, number 2, we want the probability that some randomly selected driver receives a ticket. We're just looking at a randomly selected driver. I just mentioned a second ago, we're just going to use these purple numbers. So we want to look at which ones get a ticket. So that's going to be here or here. So we got 0.072 plus 0.028, which gives us, I think, 0.1. Let me check. It does. So that's it. Now, this is assuming on a free response, this is acceptable for your work, but that's assuming, right, the tree diagram is there as part of your work. And if we're going to pull numbers out of a tree diagram and add them, we got to show that addition. So like earlier, right, it was implied multiplication across branches. Like this addition is not implied. You have to show that. That's it. Now, I do want to mention that you could answer this question without a tree diagram. What you'd have to think about here is for the probability that someone gets a ticket, right, receives a ticket. That could happen 2 ways. You could be speeding and get a ticket, or you could be not speeding and get a ticket based on the information given. So you could do the problem without the tree diagram. Now I just kind of have a lot of information to sort through. So first I have to think, all right, the probability someone's speeding is 0.6 times. Then I got to remember, all right, there was 2 ticket probabilities, but if they're speeding, the probability they get a ticket's the 0.12. Or means add. Now I got to think, all right, 60% of people were speeding, so that means 40% of people are not speeding, and means multiply here. And then, all right, the probability you get a ticket, if I know you're not speeding, then the probability you get a ticket was 0.07. Right, so you could do this problem without a tree diagram. For me, I like to visually organize that information, but if you can keep track of that stuff, you can use like the words and kind of just plug in the numbers and get the correct answer. And lastly, I mean, that's the same thing we did, right? 0.072, that was just 0.6 times 0.12. And 0.028, that was just this 0.04, this, sorry, 0.4 times 0.07 right there. Right? So it's the same thing. It's just how you set it up. All right, let's get into the tougher one. Obviously, number one's after number two. So here, what's the probability a driver who got a ticket was speeding? Try it out. I should have said that before, but hopefully it's obvious by now, right? Before I start, you pause the video, you try it. That's how you learn stuff. Try it, and then if you got it right, that's going to stick with you more than if you just robotically follow along with me. But anyways, on the first day of conditional probability, I told you the biggest challenge is going to be recognizing conditional probability, especially when it's blended in with everything else, and especially when the word given isn't used. Did you realize this was conditional probability? So for any conditional, I like to write out that conditional notation first. So I like to write out in words here, probability of blank given blank. And this given thing is what we know is true. Which event we know occurred. What do we know about this driver? Right? We know they got a ticket. So what's probably the driver who got a ticket, right? Given this driver got a ticket, we want to know what's the probability they were speeding. Now that should probably be a high answer, right? Because I don't know. Do I think that? Do I think it should be a high answer? I don't want to make the video too long, but that's something to think about. I don't want to waste more time. So conditional probability, right? Like on the exam, we might see this formula: probability of B given A equals probability of A intersect B over the probability of A. So this formula is going to be given. We just have to know how to read it. And right, this is telling us, right, this means and. So this is A and B in the numerator. So for us, in our numerator, we want the probability someone's speeding, and ticket, right? So I like to write the blue notation here first, because then it just, to me, becomes plugging numbers into a formula, right? The numerator is always both A, or the overlap, or in this case, I'd like to think A and B. So the numerator is speeding and ticket. So before we even worry about the denominator, which of these numbers, and again, remember earlier I mentioned you're going to do all the problems using these values, right? There'll be other ways to take shortcuts as we get more comfortable, but for now, probability when someone's speeding and gets a ticket, so that's this number right here. So that is our numerator. In the denominator, right, oh, here we can see it's the A, the given thing. So our denominator is going to be the total probability, or the total percentage or proportion of people who get a ticket. Now, of course, we know that's 0.1, but if we hadn't already answered the previous question, we look down here. So the total for a ticket, that's this spot, speeding and ticket, or this spot, not speeding and ticket. So in the denominator, rather, we're going to have 0.072 plus 0.028. Now, of course, I know I could have just written the 0.1 we figured out a second ago. The reason I didn't is when you're doing conditional probability with tree diagrams, if you just use the far right numbers, and if you show the addition in the numerator, you're always going to see the number in the numerator repeat in the denominator, right? This is always going to happen. It might not be the first one. I could have written it as the second one, right? But this number is always going to be part of the denominator as well. And if it's not, you made a mistake. I wonder why that's always the same in the numerator and denominator. Think about it. Think about those words we got in red and green. Anyways, from here, so we've got 0.072 over 0.1, and that gives us, turns out I wrote down all the work, but like, I mean, I feel like I shouldn't need a calculator to do this, 0.072 divided by 0.1, but you know, YouTube pressure. So 0.72. But I promise I did the whole problem, right? It was right there, but I just didn't write the final answer. I guess that means I didn't do the whole problem. So the probability someone's speeding, given they get a ticket, is 0.72. It's pretty likely someone was speeding if we know they got a ticket. That's what that tells us. I'm not trying to say that's easy, but we could do that. Write the blue notation in words. Write it. I don't know. That might have been weird. All right. Number 3. Obviously after number 1. Pause it. This probability a driver who was speeding got a ticket. Is it conditional or is it just an and something? Yeah, conditional. That's right. What's the probability that a driver who was speeding? This time, we know we're given the driver was speeding. And from there, we want to know what's the probability they got a ticket if we know they were speeding. I wonder what the answer is. And hopefully you're thinking to yourself like, wait a second, we know that already. We know the probability that a driver gets a ticket if we know they were speeding is 0.12. The reason I still put this question here is because you might not have realized that. And I want to just make the point that if you start just working with the formula, you're still going to get the right answer. Numerator, right? Ticket and speeding. So that's going to be this, right? Speeding and ticket, ticket and speeding. So we got 0.072. Our denominator, we know this number should kind of repeat. I did it again. What is happening? Sorry, it's really frustrating. So denominator is going to be the total that's speeding. Oh, why did I use blue? So down here, which numbers are speeders? Nope, not them. They weren't speeding. That weren't speeding. Oh, they were, and they were. So the denominator here, we see that repeat plus 0.528. That gives us 0.6 in the denominator. Got to keep my colors consistent. And 0.072 divided by 0.6 gives us, I don't need a calculator. Better be 0.12. Right, because we know we already knew that was the answer. That's the probability a driver gets a ticket given we knew they're speeding. So that's what I mean. That's what I mean by sometimes you can take shortcuts as you understand the tree diagram more and more. But if you don't and you're a little more hesitant, right? If you just are a little more robotic and go through the formulas, it's going to work. Two more. What's the probability that a driver did not receive a ticket? Conditional? Do we know anything about this driver? I mean, we know they're a driver, but everybody in this problem's a driver. So we know anything about tickets or speeding? Nah, we just want the probability they did not receive a ticket. And hopefully you're looking at this tree diagram and that's this spot or, oh my goodness. Oh my goodness. There's a typo in here. I'm not going to redo the whole video. Hopefully you saw that earlier and then fixed it in your notes. That's terrible. Anyways, these people didn't get a ticket either now that I've labeled it correctly. So we're just going to add. And now if you're like rushing on the AP exam, like show your work that way. Circle the two numbers and write the addition and tell me that that equals 0.9. Or write it up, What's another way we could have answered this question just based on what we've already done today? Earlier, I think we figured out probability that someone was speeding was 0.1. So the probability that they're not speeding is the other 90%. Man, it all connects. All right, last one. I can't stop thinking about that typo. It's totally blowing my mind. I'm really sorry about that, guys. Like, geez. All right. What's the probability the driver was not speeding given they did receive a ticket? And of course, this time you know it's conditional because we got the word given. I saved the obvious one for last. The obvious one for last. Why can't I speak tonight? So here we want the probability the driver was not speeding given they did receive a ticket. That seems kind of messed up. Oh, no, wait, maybe they were running a stop sign or something. I'm not going to fix that. So numerator, always the same, right? Both. Numerator, not speeding, and ticket. Denominator, what was I doing? Denominator, the total that received a ticket. So what's the probability a driver was not speeding given they did receive a ticket? So in our denominator, we want the total that received a ticket, which we at this point probably remember is 0.1, but if we don't, we're looking at these two spots, ticket and ticket, or I should say ticket or ticket because we're adding. And then the numerator, we've got not speeding and get a ticket. That's going to be our 0.028. We see this number repeat as we expected, and that gives us 28%. 28% chance a driver was not speeding if we know they get a ticket. Of all the people who got a ticket, 28% of them were not speeding. That means of all the people who get a ticket, 72% were speeding, So it seems like speeding is the most common kind of ticket. All right, that's it. So you got some optional practice. Optional. Do it. Do it. It's about learning. It's about getting better. It's about practicing. It's not about I told you to do your homework, so you have to. It's about you got to have the desire to do better. So do that. I'll see you guys soon. And have a great weekend. And I always start saying bye before I stop the share. So yeah.